go to the equivalence point. The equivalence point is, we're almost always going to titrate. You titrate strong acid and strong base. We're going to be doing quite a few that are going to be weak acid and a strong base, or weak base and strong acid. They're harder, so they show up more. You say you neutralize something when you're adding, when your moles of your strong acid equal the moles of the weak base you're titrating against. So let's say that you had hydrofluoric acid, that's your weak acid, and you're going to titrate it. That means you're going to add moles of something like sodium hydroxide until you've used all of this up. So if you have 1 mole of hydrofluoric acid, you're going to have to add 1 mole of sodium hydroxide. When you've done that, you're at the equivalence point. So the equivalence point, moles of the weak thing equal the moles of the strong thing. So this could be weak base, strong acid as well. And at that point, what happens is, well, we know if we've got 1 mole of each of these, let's go ahead and say strong reacts 100%. So I'm going to take the H off of that acid, and I'll have fluoride, and I'll put the H over here. We know sodium doesn't do anything, it's a spectator ion. Sodium ion doesn't do anything. So I'll add hydrogen to the hydroxide, and I get water, which isn't going to affect my pH. So if I have 1 mole and 1 mole, I'm going to use up the whole thing. So I won't have any of either of these left at the equivalence point. And I started with none of the conjugate, none of that product. I make 1 mole. So in the end, the only thing that's going to affect my pH is going to be the conjugate weak base of this weak acid. So all I have is I have a weak base. And at that point, to find the pH, well, I've got a weak base. I take the weak base, I put it in water, and I do some equilibrium. I use my Kb because it's a base, find out how much hydroxide is produced, and then I can find the POH and then the pH from that. So these guys, that's the abbreviated version, so you can see these guys are a pain. When you're titrating, you've got a strong thing and a weak thing. So the strong reacts 100%. So you start off with that ICF final table, and you're using moles. And then at the end, you see what you have. Don't forget to add volumes together, because you had some volume here, some volume here. In the end, well, they add up. I would take these moles and divide by the total volume to get my molarity of this weak base. And then you do the next part, which is the ICE table, the equilibrium for that weak thing. Let's try one. So I have, what is the pH at equivalence point? So when I have equal moles of 1 molar sodium hydroxide is being added to 100 milliliters of 0.5 molar hydrofluoric acid. I'm going to write out this equation. I've got hydrofluoric acid. I'm adding sodium hydroxide. Oh, that's the one I picked as my example. They react 100%. So I'm going to have fluoride, and I'm going to have water. Okay, so what do I have initially? What's my change? What's my final? I can see I have 100 milliliters, so that's 1/10 of a liter, and I've got 0.5 moles per liter, so 1/10 of that 0.5 will be 0.05 moles. I have 0.05 moles of hydrofluoric acid. I'm going to have to add 0.05 moles of base to get to my equivalence point. So the next question is, what's the volume of this going to be? We'll do that at the end when I'm trying to find out the volume of this guy. So I know I've got this 1-to-1 ratio. I'm going to use up all of the moles from each side, and I'm going to make 0.05 moles there. So I'm left with no hydrofluoric, no sodium hydroxide, and 0.05 moles of this weak base. That's all I have is this weak base. So I know I'm going to take the weak base, I put it in water, and I find out to what degree it's going to react with the water, because weak things don't go all the way. HF plus, took an H off, hydroxide. Okay, so now I've got an ICE. For ICF, I use moles. For ICE, I use molarity. I need the molarity of that. So the molarity of the fluoride is equal to the moles, which is 0.05, over the volume. So I had 100 milliliters of this guy. I'm adding 1 molar sodium hydroxide. So the quick way to do this, I needed equal moles. this is twice as strong, I'm going to need half the volume, so I'm going to need 50 milliliters. So it's going to be 150 milliliters or 0.15 liters. But I'll show you the dimensional analysis because I know that's what kids like. So I've got 0.05 moles of this hydroxide is what I need. And for every 1 mole, there's 1 liter. Okay, so that's 0.05 liters. So 0.05 liters plus that 100 milliliters, which is 0.1 liter, is what gave me 0.15 liters. All right, so that is a molarity of, that's a third. Okay, so that's my fluoride. I have 0.3. I want to see what it does. I don't care about this. I'm going to have this minus X. Start with nothing over here. And I gain X. This is a weak base, so I'm going to use the Kb expression. Kb is going to be products over reactants. So let's see, actually I know the Kb too. Oh, also, no I don't have to solve for that. X squared over 0.3 minus X. And unfortunately, I know the Ka value just because it was on the problem before. I have to solve for the Kb, and I can do that down here. I know that Ka times Kb equals Kw. So Kw divided by Kb, or divided by Ka will give me my Kb. So let's see, I'm going to divide both sides by Ka, divided by Ka. Okay, so Kb is Kw over Ka. Kw is that 1 times 10 to the negative 14th. That's a constant. It's what the concentration, or the product of your concentration of ions is always going to be in water, hydroxide and hydronium. The Ka for hydrofluoric acid, it was in the problem before, and it would be on any AP problem. 7.2 times 10 to the negative 4th. They're in your textbook too. You can look them up. So that divided by that, I get my Kb for fluoride. I have 1.38 times 10 to the negative 11th. So now I have a Kb. I'm just going to plug that straight in. 1.38 times 10 to the negative 11. I'm sorry, this is messy. Smartboards are awesome, but they lack a little space. Okay, so now I can say X is going to be a small number. And my rule for do I get to ignore the X, which I will, and you can, is that this is at least 100 times bigger than that. Most definitely. It's much more than 100 times bigger. So this minus this really small insignificant number is still really is 1/3. So I'm going to go ahead and multiply both sides by 1/3. Really divide that by 3, and I'm going to square root both sides to get the X by itself. And what I got was X is going to be 2.15 times 10 to the negative 6. And my X is my hydroxide, isn't it? Okay, so since I have my hydroxide, I can use that equation POH, and my concentration of hydroxide, equals negative log my concentration of OH, which is 2.15 times 10 to the negative 6. Great. POH ends up being 5.667, and we know pH plus POH always equals 14, so 14 minus that tells me that pH equals 8.33, and then that is 2 sig figs, and that's good. So that's the pH of this thing when I have neutralized hydrofluoric acid with some sodium hydroxide. One thing you'll want to do to see if it makes any sense is I do have this weak acid, and I'm adding a strong base to it until I have equal moles of either. So the equivalence point should be a little basic because there's more base than, strong base, weak acid, and equal moles of each. Excuse me. And this is slightly basic. So I'm happy.